Aloha. In this problem, we're told that the maximum pressure drop that a person's lungs can achieve is, which I'm going to label, and this is a gauge pressure, the delta P gauge. Maximum is 75 millimeters of mercury, and this is a negative pressure change here. That's how much the lungs can reduce the pressure. And we want to find what I'll call H max, which is the maximum height of water that can be basically sucked up or like pulled a straw. And this information about the maximum pressure drop in a person's lungs. So the water is going to raise up in the straw when the person is dropping pressure in the lungs and sucking on it. So we can write down an equation that comes from Bernoulli's equation. So we have that this pressure difference, and we're considering the case where this is maximum to consider the maximum height, will be the density times the acceleration due to gravity times this H max. So that comes from Bernoulli's equation. And in that equation, we have in one initial case, so then before the person starts sucking on the straw, and rho is the density of the fluid. So in this case, this is water. And there's a kinetic term, like 1/2 rho times the velocity squared. But when we're writing down this equation, we're just considering before and after the person has started sucking on the straw and when they reach the maximum. So there's no velocity, and this will be equal to the same terms in the final state when the water's all the way up the straw. So then you can just rearrange this algebraically, and H will be y1 minus y2, or y2 minus y1, however you define it. So you can see this is Bernoulli's equation without the kinetic terms, and that's how we get this equation here that we're going to use. And we can just rearrange this equation so that we have it as an equation for the maximum height, which is what we want to find. So that the change in pressure is something given to us. The density we use is the density of water. So I'll write that as rho water times G. So we can just plug these numbers in. We have 75 millimeters of mercury. And we want to convert this to SI units, pascals, which are newtons per meter squared. So you can find this in chapter 10, this conversion factor. And 1 millimeter of mercury, there's 133 pascals. And the density of water, 1,000 kilograms per meter cubed, also in a table in textbook. And for G, we use 9.8 meters per second squared. So we'll have an answer that's in terms of meters. Since here we'll have these units all canceling out with the newton per meter squared in the top. And you should get something that approximates to 1 meter.